Today we're going to go over the last lesson in our course, which is the last topic that we're going to cover for inferential statistics. We're going to learn about one of the most important tools in statistics, and that's called linear regression. And this method is when we want to create a relationship mathematically between two quantities, like miles and hours. And so miles might be one quantity, and then hours might be the other quantity, and we want to see the relationship between those. So the goal of linear regression is to find what's called the line of best fit. And there's a way to do that by hand with formulas, but we're going to let GeoGebra do that process for us to save us some time and arithmetic. But this line of best fit is the line that comes the closest to all the data values. So we collect the data, but then we use mathematics, this process called linear regression, to find the line that comes the closest to all of those data points. So then we can use that line to estimate other values in between or a little bit beyond what our data values are. So we have our equation, our general form that we're going to use in this case is y equals mx plus b. And this is called slope-intercept form because we can see the m and the b clearly. So this is the form that we're going to be using. So y is the dependent variable, and that's what we're trying to predict. X is the independent variable. And these are other ways of saying these variables. We have the predicted, sometimes we call it the response variable or the explanatory variable. And then m is the slope and b is the y-intercept. But before we start making predictions, we have to talk about a couple of different things that are very important. The first thing, correlation does not imply causation. That is a fancy way of saying if you find a linear correlation between two variables, that doesn't necessarily imply or mean that whatever the x quantity is causes or affects the y value directly. So here is one example that we can look at to help us understand. We have ice cream sales and drowning deaths are positively correlated. So they're the relationship between them. But that doesn't mean that ice cream sales causes drowning deaths. They're the relationship between them, but one doesn't cause or affect the other. The real reason is the temperature. So in the summertime, ice cream sales go up, and in the summertime, at the same time, people go to the beach, so the number of drownings is going to increase versus when it's wintertime. So at that same time, you're going to have both of those values increase. So there is a correlation between them. They're both going to increase during the summertime. However, ice cream sales do not cause drownings. So here's another example. Shoe size and reading level may be correlated in children. However, shoe size does not cause better reading. Age is the real variable here. So what we're really looking at is kids get older, their feet get bigger, so their shoe size goes up. And also, as they age, they get better at reading, so their reading skills go up. But that doesn't mean that their shoe size affects directly their reading level. So there is a relationship between them, but one doesn't cause the other. So it's always important to be careful when you're interpreting what we call a linear relationship. So that's what we call correlation does not imply causation. Okay, the next thing that we need to talk about that's really important before we start making our predictions, we need to talk about what's called the domain and the range. Now, we've used these things before, but we've never put a label on it. So domain, that's the set of all the x values for a function or a relationship, and the range is the set of all the y values from the function. Or in this case, we're going to talk specifically about the line. So when we use a model to make predictions, When we go far outside that range, that's called extrapolation, and sometimes it can lead to unrealistic predictions or something that doesn't make sense. So when you create your domain for your linear equation, for whatever the situation is that you're trying to model, you want to make sure that you pick a domain that makes sense. So let's look at an example of this so that you understand what I mean. Suppose a company collects data on how many orders they receive during every hour during the workday from 9 to 5, and it creates a linear regression model. The data shows a steady decrease in orders from 9 a.m. until closing at 5 p.m. If we use the model to predict the number of orders at 10 p.m., the result might suggest a negative number of orders, which makes no sense. The model was only valid between 9 and 5. So if you look at the graph here, these are the hours. Now it doesn't list the hours that you see on the clock, it's military hours. So here's 9 o'clock, and this is the number of values that they observed for their orders. And then if you come over to 10 o'clock, that dot is the number of orders for 10 a.m. And then here's noon at 12. And then when we get to 13, it's 1 o'clock, 2 o'clock, 3 o'clock, 4 o'clock. And then when we hit 17, that's 5 o'clock. Okay, so if we continue to go past 5 o'clock, this wouldn't make sense for a couple different reasons. One, they're only open from 9 to 5, so they won't be processing any purchases after 5. And the other reason, if we get past the 21st hour, between the 21st and the 22nd hour, it's going to start to drop below the x-axis, and it doesn't make sense to have negative orders. So when we create a linear model, we want to make sure that we're creating the right domain. We don't want to go past a certain point on the line that's not going to make sense. So I would say that my domain for this model would be from x is equal to 9 to x is equal to 17. And we wouldn't use it outside of that interval. Now, let's look at our first example. I have my tables for example 1 and example 2 already preloaded. So if you don't have those in there, go ahead and pause the video and put in your values. Okay, now let's start looking at example 1. It says electric vehicle charging and monthly electricity cost. A family tracks the number of times they charge their electric vehicle in a month and records their electricity bill for the same month. So when X is 1, their electric bill is 108. When they do 2 charges, it's 110. When they do 3 charges, it's 119, etc. So the first part of this question, it says we want to find the linear regression model, meaning the line best fit. So we're going to find the line that comes the closest to all these values when they're graphed. And we want to find it in the form y equals mx plus b. And then we're also going to state a good domain for this model. So when we perform linear regression using GeoGebra, we're going to do it the same way we found the r and the r squared from the last lesson. So I'm going to highlight my values for that table. I'm going to hit the histogram button. And then I'm going to choose 2 variable regression analysis. Okay, so when we look at this graph, if it says none in your case or something else, make sure you choose linear. So here are the points that are graphed, and we want to come up with a line that comes the closest to all those points. So when we choose linear, you're going to get that equation down here. It says y is equal to 5.0833x. So this number in front of the x, that's the slope. And then we have our x variable where we can plug values in. That's our variable. And then we have plus 103, that's our b. So you can see a little bit underneath 105 is where it crosses the y-axis. That's where it crosses at 103. Okay, so let's write this down. I'm going to replace my m with 5.0833. 5.0833. and my value of B is 103. Now, for my domain, the number of charges we have is from 1 to 8. We might want to go out maybe to 9 or 10, but we don't want to go way too far out because the model might not make sense. So, and again, this is subjective. Everybody might come up with slightly different answers. Someone else might come up with, oh, I want to go out to 9.5, or I want to go out to 10.5. So as long as you're within a reasonable range, it's okay. Now for the homework, to make sure that we're all on the same page and we're all selecting the same values for the purposes of grading, I made the domain multiple choice. So you just pick the one that is the best for that model. So I'm going to put 1 to 10. All right, now the second part says find the correlation coefficient of R and interpret its value. And this is what we practiced in the last lesson, but now we're going to tie that into what we're doing today. Remember, R represents how close the data values are to the line. Is it a good fit? Is it an excellent fit? Is it moderate? Is it weak? And the closer we are to 1, whether it's -1 or +1, that's going to give us a perfect model. So because these points are pretty close to the line, I'm going to say it's going to be in the 90s. So to find our R and the R squared, I'm going to come up and choose the sigma with the X to show statistics. And so here's the R value. I'm going to put that in there. So I'm going to put in R is 0.9866. Now we have to interpret that. Because R is positive and it's really close to 1, I'm going to say there is a strong positive linear correlation between the number of charges and the electric bill. Okay, I have to adjust this so you can see it. It ran off the screen. Sorry about that. Okay. Now for R squared says it's 0.9735. Now, remember what the coefficient of determination represents. It's how much of the variance in the y variable can be explained by the change in the x value. So we're going to say 97.35% of the variance of the change in the electric bill can be explained by the change in, whoops, I'm running off the page again. Okay, can be explained by the change in the number of charges. Now, whatever is left over from that is what can't be explained. So that's due to randomness. You might have an outlier that's throwing something off, or you might have a lurking or confounding variable that's something that you didn't anticipate. So the rest of it is going to be what you can't predict. So this is pretty good. 97.35% of the variance we know is because of the change in X. All right, we're done with this, so let me close it out. All right, now the slope. We need to identify the slope and interpret it in the context of this question. So we got a slope. If you look up here, the slope is the value that's in front of the x. So we have a slope of 5.0833. That's the value that's in front of your x. Now, even though we didn't write it in there, this 5.0833 is over 1. Okay, so 5.0833, that's the change in Y, which if you recall, that's the change in dollars for the electric bill. And then 1, which is downstairs, which we're not showing, but we know it's there, that's the change in the number of charges. So our slope is 5.0833. And our interpretation, now because the slope is positive, that means as x increases, y increases. They're both going to increase together. So we're going to say for each charge, the bill increases by $5.08. We're going to round it to dollars and cents since we're talking about it in the context of money. All right, now part E says this is where we're going to use our line to make predictions. Part E says predict the electricity bill if the vehicle is charged 6.5 times a month. Now, if you notice, we don't have a data value for 6.5. We have one for 6, right? If we come up here, we have that 6 is 133, but we don't have one for 6.5. So that's why we're using the line, our equation, to estimate what happens between the 2 points. So our equation is y equals 5.0833. Now I'm going to put in for x 6.5. How do I know not to put that in for y? This is why it's so important to understand what your variables represent. This question states that we're talking about a vehicle that is charged 6.5 times in a month. So that is our x. And then we're asked to predict the electricity bill, which is our y value. So this is what is unknown, what we're trying to find. So when I write my line, I'm going to replace x with 6.5. Okay, now, if I work this out on the calculator, I'm going to take 5.0833, multiply it by 6.5, and then add 103. When we do that, we're going to get 136.0417. So what this means, let me write this down. We estimate that if there are 6.5 charges, the electric bill will be approximately 136. We're going to put this in terms of dollars and cents, so it'd be in 4 cents. Now part F says, estimate how many times the vehicle was charged if the electricity bill was $130. So if we look up here, $130 is going to fall somewhere in here if we use our data values. It's between 125 and 132. So we're going to guess that it's somewhere between 4 and 5. That's where it should be, somewhere in that area. But to find it based on the line, we're going to use our equation. We have y is equal to 5.0833x plus 103. So here's our equation of the line. Now, the question gives us the amount of the electricity bill, which is our y value, and it's asking us to predict how many charges that would be. So because it's giving us the electricity bill, which is the y value, I'm going to put in 130 for the y value. And then I have to solve based on this. I have to solve for x because that's what we're looking for, the number of charges. Okay, so in order to solve this for x, we first need to subtract. Let me put this up here next to this. We need to subtract 103 from both sides. So when we do that, if I subtract 103 from both sides, this is going to disappear, 103 on this side. So on this side, I'm going to take 130 minus 103. So that's going to leave me on this side with 27. And then on the other side, that's going to leave me with 5.0833x. Now, to take the last step to solve for x, I have to divide both sides by 5.0833. So when I divide both sides by 5.0833, we get that x is equal to 5.3115, which is close to where we predicted. Based on our data, we were thinking it was going to fall in the 4 or 5 area, and that we got pretty close to that. All right, so what does this mean? This means we predict that if the electric bill is $130, there will be 5.3115 charges. Now, in the context, we probably would round it to the nearest number of charges. We might say, since it's closer to 5, about 5 charges. But that's based on the mathematics from our model. So if we look at 130 on the graph and we come over this way and we come down, that's a little bit over 5 right there for the x value. All right, let's look at the next example. Now again, I have my values preloaded. That's in my C and D column. If you do not have those preloaded, take a minute, pause the video, and enter those into your spreadsheet. All right, so this example is hours on social media compared with sleep duration. A group of teenagers reports how many hours they spend on social media each day and how many hours they sleep at night. So X is the number of hours for social media, and Y is how many hours they sleep. In part A, we're going to find the linear regression model in the form of y equals mx plus b and state a good domain for this model. So I'm going to highlight my values for my chart. I'm going to choose again the histogram button and use 2 variable analysis. And now I get the new graph and the new equation for this set of data. So if you look down here, we have our line for this question. Our slope is negative 0.2857, and my y-intercept is 8.2857. Now for the domain, if you notice here, this is where x is 0. I don't want to go to the left of 0 for my x because it doesn't make sense to have negative hours of social media use. So I'm going to use my minimum as 0. And then when I come out this way, somewhere between 7 and 8, it crosses the x-axis, and then what we would have is negative hours of sleep, which doesn't make sense. So I'm going to stop at 7. We don't want to go past 7 too much because then that's when sleep becomes negative, which doesn't make sense. Now someone else might choose to go from 0.5 to 7.2 or something like that. But again, for the sake of grading and everybody being on the same page, I made those questions multiple choice. All right, so for parts B and C, we need to find the value of r and r squared. Whoops, I switched those. Let me fix it. So this is our r squared. Okay, so to find our values of r and r squared, we need to choose the statistics button. So after we click the statistics button, we can see our r is negative 0.9 0.9765, and the value of r is, or r squared, excuse me, 0.9535. All right, we wrote that down. I don't need that anymore. I'm going to swing it over because I don't like it being so squeezed in there. All right, for our interpretation, this is a negative r value, but it's still really close to 1. It's close to -1, actually. So this is going to be a strong linear correlation, but it's going to be a negative correlation, meaning as x increases, y decreases. So we can check that. As x goes up in value, look what happens to y. Y goes down in value, and you can see that on the graph and in the chart here. So I'm going to say there is a strong negative linear correlation between the hours on social media and the number of hours slept. Okay, now for r squared, that's our coefficient of determination, I would say about 95.35% of the variance for the sleep duration is explained by the change in the hours of social media use. Okay, now the slope, that's the value that's in front of the x. So our slope is negative 0.2857. Even though we don't have a 1 under there written here, we know it's there. So this is actually negative 0.2857 over 1. The negative 0.2857 is the change in y, so that's the change in sleep duration. And then the 1 underneath is the change in social media hours. So our interpretation for each hour increased in social media use, there is a decrease, because it's negative, of 0.2857 hours of sleep. Now, in part E, it says, predict sleep duration for someone who spends 3.5 hours on social media. So this is where we're going to use our model to figure this out. So our equation is y equals negative 2 So our equation is y equals negative 0.2857, and then we have our x, plus our y-intercept, which is 8.2857. Now, what does this 3.5 represent, and what are we trying to find? We're trying to predict the sleep duration, so we're trying to find the value of y, that's our sleep duration, given the number of hours on social media. So we're given 3.5, that's our value of x. So we're given the value of x, and we're trying to find the value of y. So I'm going to put x in here as 3.5. And when I work that out, I get y is equal to 7.2857. So this means we predict that a person will get approximately 7.2857 0.2857 hours of sleep if they spend 3.5 hours on social media. All right, the last part says estimate how many hours on social media would result in 7 hours of sleep. So our equation is y is equal to negative 0.2857, and then we have our x, plus our y-intercept, which is 8.2857. Now, in this case, what is provided to us is the number of hours of sleep, and we're asked to predict or estimate how many hours this would be on social media. So that means 7, that's our sleep duration. That's going to go in for my y value. So I'm going to put in 7 here, and now solve for x. So in order to do that, I have to subtract 8.2857 from both sides. When we subtract 8.2857 from both sides, whoops, that's going to give me on the left side, that's going to give me a negative 1.2857. On the right side, we're left with negative 0.2857x. So now to solve for x, we have to divide both sides by negative 0.2857. When we divide both sides by negative 0.2857, we get that x is 4.5002. Let me put an x equals in there. All right, now what does this mean? This means we predict that if a person uses social media for 4.5002 hours, they will get about 7 hours of sleep. Gotta fix all my typing errors here. So to sum up, linear regression is the process of using mathematics to come up with a line that comes the closest to all of your data values that you collect. Then you can use that line to make predictions and estimations. And you have to be very careful about how you choose your domain, because you want to choose it in a way that it's going to make sense with the situation. And the other important thing was, don't forget, when you're looking at this, the quantity of x, whatever that represents, doesn't necessarily cause the change in y. We're just stating that there's a relationship between those two quantities.